Yeah, I think I did. Okay. Let's go from current slide. Yes, I did. I did last time. I forgot you weren't here. And do you have graph paper? Huh? No, I mean, I can give you some. It just, if you prefer yours rather than the stuff I have. There's quite a bit of graphing on this. You want graph paper? You got it? Okay. The first 9 are all graphs. Okay. So you can spread them out however you want to. But I've got graph paper. I'll be glad to share it with you. Let me turn on the projector. And also, let me go over these announcements first, and then I'll answer Angelica's question. I don't know if you remember what it was, but I'll go over that with you. Last week, we finished the first mini-term. So if any of you were in a first mini-term course or know of someone who was in a first mini-term course, they were very late opening the student course evaluations for that. So please tell them, or you yourself, please do the student course evaluations for that first mini-term course. They are important. They're valuable to us. Very valuable to me as a department chair. I use those to doing my evaluation of my instructors. So I really pay attention to those, and I think most people do. All right, there was that. But also with that was the fact that we're reached midterm. And this class, of course, one of my best classes ever, I've only received, thank you. Did you finish this time?
Yeah. Thursday, I can see the updated grade.
I'm sorry?
Thursday, I can see the updated grade.
Yeah, you can see your grades anytime. But I'd rather not during this class, but anytime. So if you just want to see the grades, you can see those anytime. Okay. All right. Before I forget this. All right. Well, I turned on the projector and nothing happened. So let me try it again. Okay. So as I was saying, this, of course, one of my best classes ever. And by the way, let me get not Nikhil. I have only 2 people have turned in research papers, and before today, only 5 had turned in the first test. I did get 1 more in today. So that means for 1, 2, 3, 4, 5, 6 people, now 5 people, I have no score at all. So if I had to do a midterm progress report for you today, it would be an F. Okay, and y'all are F students, so please get me something. What's that? I can't hear you.
Say the names you turned in.
Change the name. Oh, say the names. Well, I can say your name if you don't mind, but not everybody minds. Yeah. You have turned in both the first test and the paper. Yeah. And 2 people have done that, and several people have done neither of those. Okay. I don't want to call out anybody unless I have permission to call out somebody. Yeah, no problem. Okay. Now, so please get me something this week. So I don't know when they're going to open that. Right now we're so busy with fall schedule that I don't know if anyone's even thinking about midterm progress reports right now. All right. Now, Angelica had a question. I guess I ought to go on and get this said. I didn't tell my first class because it didn't come up, but I guess I'll go and do it. You know, Tuesday I had a doctor's appointment, and I couldn't be here for class on Tuesday. Thursday I had a meeting in Tuscaloosa I couldn't be here for. So I've missed seeing y'all for more than a week now. 2 weeks no, a little less than 2 weeks. Now my doctor's appointment. Both the nurse and the doctor got really concerned about my blood work. Now I'm on they're called monoclonal antibodies, and what they do, that's what the treatment is, and what those are supposed to do is attack the specific cell that is, multiplying too fast, it's in leukemia. And the drug I'm on now is doing a superb job of that. I went through a harsh chemotherapy back in 2009. It wasn't too bad, but it was 2 drugs. It knocked the counts way, way down, but they started coming back. Then I got on the first of these whatever I just called them, I just said the name and I can't say it now. But anyway, I got on the first of this. It did okay for a while, but then it didn't do too well, so they put me on another one. It did about the same as the first one, but not as well as long. And I think this is the 3rd one of these monoclonal antibodies. That's what I'm trying to say. And this one, my goodness, it knocks those white cells right down, sometimes below the normal range. So it's been doing a great job. Now, all of the drugs, the chemicals and the monoclonal antibodies, all of them, they also do collateral damage to red blood cells and platelets and other things like this. So I'm kind of used to that. They don't hit them as hard, but always the numbers go down some. So basically, ever since I've been on treatments, my red blood cells have been slightly anemic, but it's not anything that one thought was serious. But this last round, this drug that does such a good job on the white cell, it knocked them. They're still in the low normal range 2 months after the treatment, so it did a really good job on them. But unfortunately, it did too good a job on the red blood cells too, so I'm very anemic right now. I didn't know this. I just thought I was old. Because I was tired. I just thought, because I'm 69, I've never been 69 before. I figured it just come with age. Well, no, I found out now it's that. But they didn't have my blood work ready when I left, and the doctor was so concerned he sent me back to the lab to get 5 more vials of blood taken out so he could do more tests to see what's happening with the red blood cells. So far, I haven't heard anything from him, but that's sort of good news, because if it was something serious, I think he would have contacted me. So hopefully everything's all right. He put me on B12, which is supposed to sort of boost your, he said the size or shape or something of the cells indicated it wasn't an iron deficiency. It was just that he thinks the proteins were attacking the red blood cells. I think they knocked out all the white cells and started looking for other cells to go after. This is my layman's view of it. So anyway, so they're somewhat concerned, but all they said was take B12, so I've been taking B12 tablet, pills every night. Okay. But then on Friday, I had a dermatology appointment, and so I went by to get my lab work because it wasn't ready when I left on Tuesday. And when I got that, the nurse looked at that and said, "Oh, your immune numbers are really low too." So not only did it knock down my red blood cells, but I don't know if y'all have heard of immunoglobulins, okay? IgG, IgM, and IG something else. They were all low. So here I am, low red cells, and now low immune system, and here comes the coronavirus. Okay, so my wife she said, if anything gets close, you're going to be working at home. So I hope that's not going to happen. So far, Alabama, one of the few states, I don't know if there's any confirmed cases yet or not, but it's few and far between, so I hope we're okay. But if something does turn up that I can't be here I can't be here, but all the things are out there. Now, that leads to the next question. What did y'all do last week? Did you do the videos? How far did you get? What section are you in? Uh-oh. SpaghettiOs. 4.8. That's where we left off, wasn't it? Okay. So do we pick up where I left off before, or did y'all go do anything in those videos? I flashed them up there and told you which ones to do. What's your verdict? Want to pick up where we left off? I was afraid of that. Okay. So much for that. So we're going to have to probably go. I don't do things very fast, so let's move along as well as we can. Now, at least this indicates we were on trigonometry and bearings in 4.8. Is this where y'all remember we left off? Okay. Now, these are used in two major areas, probably some others as well. One is surveying. I don't know if you've ever seen an official survey of a plot of land, but everything is given on angles and distances, and the angles are from true north, you know, so or possibly gravitate. Goodness, where my words are leaving me today. Magnetic north, either true north or magnetic north. But survey uses angles big time. I mean, to tenths of degrees, you know. In navigation, and this is at least two types of navigation. I was in the Navy. We used it all the time. You had bearings and things all the time referring to a ship, contact, an aircraft, whatever. You were always using angles for that. But also in aircraft navigation. If you've ever noticed in airports, if you've ever noticed when you're coming in a plane, there'll be numbers on certain runways, and those are the angles for true north. Okay? So there's angles are everywhere in surveying and in navigation, both air navigation, sea navigation, not so much land navigation, unless, of course, you're in uncharted areas that there's no roads or other things you can go on. So anyway, they use bearings. Now, in trigonometry, almost always our standard is the positive x-axis. And we almost always measure our angles from that in a counterclockwise direction. If you go clockwise, it's a negative angle. Okay? That's trigonometry. That's standard. Goes to the course. In terms of bearings, however, a bearing measures the acute angle. So when you're measuring from the positive x-axis, anytime you get past 90 degrees, you're in an obtuse angle. You get over here, you're even more than that. Negative angles here, well, in bearings, you always refer to an acute angle only that a path or a line of sight makes from a fixed north-south line. So if I'm here facing north, and this is just guessing, approximately north, this way. Okay, if I'm talking about that bolt right there that's holding the board on the wall, then that would be from true north, an angle of about 85 degrees. Okay, an acute angle. If I talked about the corner of the door up there, true north, that would be, okay, an angle to that. If I was talking about the latch on the window there, I go due south and do a acute angle there, or that eraser up there would be that acute angle there. So it's always, thank you. Did you finish?
Yes, sir.
Excellent, thank you. Okay, so we're always talking about an acute angle that a path or a line of sight makes with a fixed north-south line. So you either choose north or choose south, whichever one gives you the acute angle. Okay, now, let's go back to my bolt on the wall right here, okay? Due north is here. To get to that bolt, I'm going east, okay? So this would be, what did I say, 85 north, the direction I'm going from, 85 degrees east, okay? Corner of the door up there, north, 50 degrees west, okay? Latch of the door here, south, 40 degrees west again, or the duration here, south, 15 degrees east. So you always have the first direction you're given is which line are you looking at? Due north or due south? Okay? Here, south. Okay? Then how many degrees from that in which direction? And south 35 east would be facing south, the 35 degrees toward the east. That identifies your angle. Okay? So here would be, if this is north, so again, in trig, we always use the positive x-axis. You don't in navigation. You don't in survey. You use the north-south axis, which usually you refer as your y-axis. So since you're doing something south of the horizontal, you do south 35 toward the east. This would be what? This one's the second. You say a letter first. What letter first? North, 80 degrees west. Okay. How about this one? North. No, you say north, 45 degrees east. Perfect. Okay. That's how you express these bearings. Okay. So does that make sense? So you're not always going clockwise or counterclockwise. You're not always starting with a positive x-axis. You're usually either positive or negative y-axis. Okay. Good deal. Thank you. Did you finish? Yes. All right. Excellent. Okay. Here's an example. This is example 5, the bottom part of page 330. A ship leaves port at noon, heads due west. Here's the port over here, must be the west coast. Heads due west, okay, at 20 knots. Does anyone know what a knot is? Nautical miles per hour, okay? What is a nautical mile? Is that just a mile? You want to know? Now, you don't need to know this to do the problem, but this is general information. Okay. Well, a nautical mile is 1,760 yards, or 5,280 feet. That's what a statute mile is. Any mile you're talking about. On the water, and I assume in the air too, you use nautical miles, especially in the water. And those are 6,000 feet or 2,000 yards. It got to a nice round number, not 5,280 or 1,760, but 2,000 and 6,000. So you don't need to know that, but that's what a nautical mile is. A nautical mile is a little bit further than a mile, okay? And so a nautical mile per hour, same speed would be a smaller number. So 20 knots would be probably close to 22, 23 miles per hour. Okay. You don't need to know that for the problem. Just know that's what you're talking about. So at noon, they had the due west at 20 knots, and at 2 p.m., the ship changes course to north 54 degrees west. They were going due west, now they're north 54 degrees west, and are heading up that way. As shown below, find the ship's bearing and distance from the port of departure at 3 p.m. So how long did they go? And they went the same speed, 20 knots, but they changed their bearing, changed their course to north 54. So how long did they do that? 2 to 3? 2 to 3, 1 hour. So how far did they go in that 1 hour? Earth to class, come in, please. Okay. How far did they go? Just 20 nautical miles, okay? It went 40 nautical miles here because it went 2 hours from noon to 2. 40 nautical miles in this direction, 20 nautical miles in that direction. Okay? That's a picture of what we're doing. What they're asking for, find the ship's bearing from the point of departure. That's going to be a north so many degrees west, basically going to be the angle right here. That's going to be the ship's bearing at 3 o'clock. And the other question is how far from point A to D will you be? The length of that dotted line. Okay? That's going to be the second point. Okay? So, obviously, at least a two-part problem here. Okay? Because you know they went 40 nautical miles due west in the first 2 hours. And we're at 20 nautical miles at some weird angle up here. So what we need to know is what the angle from here to here is, from here to there is. Okay? Now that's not going to be immediately obvious. And then the second thing is the distance. So what do you want to go for first? Okay? Okay. Now, let me just, I think I understand what you're saying. They're naming this angle here A, and this angle A from north to west, that's going to be the angle of our answer. But this isn't the angle of a triangle. This angle A of the triangle is going to be this little angle right here. But it's easy to get the angle we're looking for from this angle here, right? Difference of 90 degrees, so they're complementary. Okay? So, we're first going to have to determine this angle, but we're not there yet. Okay? Now they have another angle here, or another point here, B, and this angle can, depends on what triangle you're dealing with. This could be the angle here, the obtuse angle here. It could be this angle here. We'll have to determine which one we're talking about. And were you talking about this B when you said B? This B? Okay. That's going to be, okay. Which angle B are you talking about? If that's the right angle B, I know what that is, 90 degrees. If it's this obtuse angle here, you just add 90 to 540. Okay? But if it's this angle B here, this little b is referring to this angle B, not this one or that. Okay? But you can still get it from that. So I agree with you. We're going to, angle B is not a bad place to start. Okay? But let's deal with this. Let's deal with this triangle right here. Okay, there's your 90 degrees. So let's use this angle B here, and we'll also determine the little b here. So how do we get the angle B here? I've been pointing my finger for those people at home. Let me get my pen set up. Okay, we're talking about this angle B here. Okay, how do we get that angle? Subtract what? 90 minus 54, is that what you said? Yes. Okay. Then what would that give you? 36 degrees. So capital B, as written here, is equal to 36 degrees. So let me write it somewhere here. 36 degrees. Perfect. Okay. Now, you know the hypotenuse of that angle. You need to know your little b here. Do you have enough information to get that? How? Okay, say that one more time.
Find the trig function corresponding between the hypotenuse and the locus B.
Okay. Give me a trig formula that says, I think, what you're trying to say. Okay, here's an angle. Okay. In reference to this angle, this, of course, is the hypotenuse. We'll call that R. Is that okay to call it R? Because that's what the book calls it a lot. What would this be, the B over here, relative to this angle and that triangle? That B would be, for this angle, 36 degrees. That's your opposite, okay? And which trig function of this angle 36 degrees relates the opposite to the hypotenuse? Or actually, let me call this the Y angle here. So which trig function relates the angle to the opposite and the hypotenuse? Sine, okay? So give me a trig equation that says that. Sine of 36 degrees is equal to, okay, well, let's go on and call it B here, B over 20. Perfect, okay? And B will be in nautical miles as well, okay? So let's go on and solve for B. What would that be? 20 times the sine of 36 degrees. I don't write very well. And someone with a calculator, punch that in and see what you get. B is equal to 20 times the sine of 36. So, second, 1.17. Is that what you said? That's, it sounds like a way too small a number. If that's 20 and this is 1, did you use what mode? Yeah, better be in degree mode. Anytime you get a number that just doesn't look like your picture at all, either your picture's really bad or you may be in the wrong mode. This is their picture. I think their picture's okay. Some of my pictures are really bad. Okay. What you get? You did? Okay, say again what you got. 1 point something? You got what? 11.75. Maybe your one's not showing up there. So B is 11.75. I'm going to go on and call that 12. I'm going to round that as 12 nautical miles. Now, does that look reasonable according to the picture here? Yeah, it's less than 20, but not half of it. But, less than 20. Okay, I'll buy that. That's going to be important later because this is your opposite side of this angle down here, which if we know this angle, we're going to know the angle we're looking for, right? So we need to know that. So maybe you want to keep 11.75. I would say 12 is probably going to be good enough. Okay? Now, what's next? The which? I couldn't hear what you said. So no. D, is that what you said?
C.
C. Oh, that's yes in Spanish. No. It might be beneficial to have. It's not necessary though. Okay? They've drawn it there. That's the hypotenuse of the big angle. But that, oh yes, you need that. That's one of the questions. The distance from the point of departure. You certainly do want that. But can you get it just knowing this, that, and that distance? I kind of don't think so. Because you don't have the whole triangle that C is a part of. What you're going to need to get that C, you already got the B, but you're going to need this length here too. And what's that length? I know part of it is 40, but this part, D, that's why I thought you said D, you don't know that. Yes, you need to find D. How will you do that?
Period. So, constant corresponding to
Okay. I hear you saying something, but I can't make out what you're saying. What's the trig relationship between this angle that you know, this side here, and the hypotenuse that you know? Come on, y'all should know these by now. Especially since you had that week of studying them. Because you didn't do anything else. I mean, no, I didn't say that, did I? Huh? What's the relationship? Yeah, the cosine of 36 degrees is the adjacent side of the hypotenuse. So let's write that down. The cosine of 36 degrees is equal to D, the adjacent side, over the hypotenuse 20. So that would be D is equal to, help me, 20 times the cosine of 36 degrees. You tell me what that comes out being.
16.8.
Did you have 16.18? So let's just call that approximately 16 nautical miles. Okay, you can keep the 16.18 if you want to. That's fine. Okay. Now, it depends on what you want to go for next. Because now you're ready to go with whatever you need, what you want to do next. You mentioned C, you want to do C, or you want to do A. Those are the two things the actual question is asking for. The bearing is going to be related to A. It's not going to be A, but it's going to be related to A. And the distance, that's going to be exactly C. So which you want to do? C. How do you do that?
The opposite side, which is lowercase b, and c, which is our hypotenuse. You gotta find
What?
you gotta find
You got to find what?
uppercase b.
Still can't hear. This angle here, is that what you're saying?
Yeah.
This, you want this angle here? Well, that's not hard to get, is it? But what, that's not going to help you. Okay, are you talking about the right angle B or the obtuse angle B?
Right.
Well, the right angle is 90 degrees. I know that. So that's not going to help you find C because that's just part of it. Well, I guess you could use, I don't think you got enough to do from. So, just tell me, you don't have to give me a numerical answer, but how are you going to go about finding C? Say again? Okay, the opposite of that angle A would be your B over here. You already know that. Just tell me your procedure. What's your thought process? What are you looking for? You're either looking for the angle A, not the one we're looking for, but this one, but you can get it from there, or you're looking for that length C. And you've got enough information to get both of them now, but you need to tell me how. Depends on which one you want to do first. Help me out, Sid.
Can you use the tangent function?
Say again?
Can you use the tangent function to find your distance?
Okay, I couldn't hear what you said. Can you use what?
The tangent.
Very good. That's going to give you this angle A because the opposite over the adjacent, and you know that part, now you know this part. So yeah, You got it. That will give you the angle A. I like that. I thought you were going for C. That's why I didn't understand what you're saying.
The 16 and 40.
So that one more. Yeah, you add the 16 and the 40. That gives you 56 is your adjacent side. Your opposite side is 12. Yeah, you can get that angle using the tangent function. How does the tangent function go? Tangent of A, we're just going to call it A, is equal to what? Okay, how does tangent go? What is tangent? And what's your opposite? What's your opposite of this angle A? Say again? That's your 12. Okay, 12 nautical miles over adjacent. No, 40 is just part of it. 56 nautical miles. Notice your units go away because you can't take your tangent's going to give you a dimensionless quantity, but that gives it to you right there. So it doesn't quite give it to you. It tells you what it is. That would be 6 over 28, which would be 3 over 14. So 3 over 14. But how are you going to get angle A? I don't think so. How do you undo a function? Inverse, exactly. So what you have here, then the A would be the inverse tangent of 3/14. I just was lazy. I didn't want to write big numbers, so I divided everything by 4. I hope I did it right. Yeah. And can you do that? Say again? 12 degrees? That sounds sort of reasonable. Okay, so this is this angle A, 12 degrees. Okay? Yeah, we're really not interested in that angle A. We're interested in the bearing, which is going to be from north. And how many degrees? Not 12. 12 is from here. How are we going to get this angle? Whoop, I did too much. Yuck. My eraser's not working. There we go. We're interested, oops, wrong question. That one. We're interested in this angle. That's your bearing. Where'd you get 36? That's way over here. That's not where your port is. Your port is back here. You want this angle right here. And you know this is 12 right there. And you know this is come on. 12 plus this angle equals what? Oh, wait. What is this angle here? When you see this right here, what does that mean? What's that? No. This thing right here? Does that look like 40 degrees to you? Second? What? Okay. It's a right angle. Of course it is. And isn't that a right angle there? From due north to due west? Isn't that a right angle? Please say yes. Okay. Now, if this part is 12 degrees, what would that part be then? Second? This part down here is 12 degrees. What would this part up here be?
Same.
78 degrees. You got it. Okay. Yes, because they add to be 90. They're complementary angles. They complete a 90 degrees. So, you can give me the bearing now. The ship's bearing is north, 78 degrees west. Excellent. We got that part done. Now we need the C. I've written over so much here, it's going to be hard to follow. A minute. Okay. I don't know how this does it. But my chair will sometimes get the cord ripped, and I've actually pulled my whole computer off the table, which is not good. Okay. So, we've got this bearing, 78 degrees. Really, that's not going to give us much of anything else. You might be able to use the 12 degrees a little bit to get C, but there's actually a better way, I think. Anyone want to make a guess? I mean, you can use the 12 if you want to, and then I'll show you the other way as well. So, which way do you want to do it? Okay. We're looking for the C. I'm just going to get it so you can see the C again. Okay. What two ways do we have to get that? Now that we know this angle, there is a way using that angle. Okay? But there is another way as well. Because what's the other thing we know? You just told me this is 12 nautical miles, and that is 56. And this is a? Okay. So what? Okay. And does the name Pythagoras ring the bell? Oh, yeah! This is one way. There's the other way. That's the hypotenuse. So that's one way you can do it. Now, the reason I like that way a little bit better than using 12 degrees is that you've rounded here and you've rounded here. Okay? But then you use this rounded here to get that, and this rounded here to get this one. So there you using rounded to get a rounded, and you round it again. So at least with the Pythagorean theorem, using this side and this that you got from this side and this side. So you are using some other things. So either way will work. But 12 squared plus 56 squared should equal C squared. So that's one way to do it. See what you get. So what I just said was C squared is equal to 12 squared plus 56 squared. Pythagorean theorem. What you get C to be? Gonna be some big numbers before you get to your answer. Say again? About 57. What say again? 0.17? Is that what you said? Huh? 27. Okay. So that's about 57 nautical miles. I'll accept that, or you can do it a little bit more precisely if you want to. Let's do it the other way using the 12 degrees here. And you can either choose to use B, which would be using the sine of 12 degrees, or to use the sum here, 56, which would be using the cosine of 12 degrees. Which one do you want to use? I really don't care. Cosine. So let's do cosine of 12 degrees is equal to, is what, adjacent, which is 56 divided by C. So that gives us C is equal to 56 divided by cosine of 12 degrees. What does that give us? And be sure you're in degree mode. Is what? Okay, 57.25. And the other was 57.28, wasn't it? I'd say 57 is pretty close, wouldn't you? Okay. Let's see how the book did it. Okay? We got our answers. It says from the triangle BCD, which is this one here, BCD, from that triangle there, you have that B is equal to 90 minus 54, which is 36. Exactly what we got. That exact. We got it. 36 degrees. Good start. Okay? The two sides of this triangle can be determined from the sine and the cosine, just like you did. B was the 20 times the sine of 36, and D was 20 times the cosine of 36. That gave you oh boy, they are going to stretch this out as far as they can. Then the tangent of A, which is exactly what you used, is B over D plus 40, okay, which would be 20 sine 36, that's from the B part, divided by 20 cosine 36 plus 40. This way you don't have as much round off, and anyway you got about 20 point or 0.209249 or 2494, but when you do an inverse tangent of that, you get A was, why in the world would they go to radians? That makes no sense at all. Okay? And then they say that's about 11.82 degrees, which we rounded to 12. So we got that exactly like they did. Why would you even mess with radians there? I don't know. Get in degree mode, do your arctangent, and it gave you 11.82. Okay? Or 12. Okay? Now, that angle will be with the north-south line, will be 90 degrees minus that, the complement of that, which we got, they got to be 78.18. We rounded to 78. Exactly like we did. See, back here, 78 degrees. Just what we got. Okay, 78.18, 78 degrees. Okay. So the bearing of the ship is north 78 degrees west. Okay. I don't know of any device out there that you can measure to the nearest hundredth of a degree. Not in rolling water and stuff like this. That's fantasy, but 78 degrees is close enough. Okay. Finally, from the triangle ACD, where sine of A, they use the sine rather than the cosine, is B over C. B was, and they did it using this, A sine 36 divided by sine of 11.82. Now, I don't like this because the 36 was a derived angle and the 11.82 were derived angles, so you're using two derived angles to get another derived angle, which is okay. They got about 56.4. We're getting 56.28225 or something like that. So still 57, about 57 nautical miles. Okay, this is important. That's your C. Good deal. All right. There is a checkpoint. It seemed like I was pulling teeth to get answers from that, and so you might want to do the checkpoint just to make sure you have a good understanding of it. Now let's move to another physical application, and that's harmonic motion. The periodic nature of trigonometric functions is useful for describing the motion of a point on an object that vibrates, oscillates, rotates, or is moved by wave motion. Any of those things can be described by a trig function. Because if something's vibrating, it's going back and forth, back and forth, back and forth. Do that as a trig function, that's what it's doing. Oscillating, same thing. Rotating, that's a trig function, or is moved by wave motion. So therefore, rotation, the Earth rotating on its axis, day, night, hours, trig function, okay? Everything, or lots of things can be described with anything that follows a regular pattern, usually can be done by trig functions. Here's an example. Consider a ball that is bobbing up and down on the end of a spring. Now here's where we start. We put the ball on the spring. It stretches the spring so far, okay? But this is where it sits in its equilibrium position, okay? When you're at rest still, it hangs right there, okay? Now what you're going to do is either you're going to stretch this spring down 10 centimeters this way and then release it, or you're going to compress the spring to 10 centimeters up and then release it. Either way, you're going to get what they call simple harmonic motion. Because if you stretch the ball down here, what you have, by Hooke's law, it's pulling upward on you. Because the spring you stretch is pulling in the opposite direction, is pulling up against you. So once you release, the initial velocity here is 0 because you're just releasing it, and then it starts moving faster and faster and faster until it reaches that equilibrium position. It's going at its fastest speed ever, okay? But it can't stop there because there's nothing to stop it, so it's going to compress the spring and go up to approximately there, and then it's going to stop it and push it back down again, and then it's going to reach maximum speed here, keep going here until it reaches here, and it's going to bob up and down and up and down and up and down. That's simple harmonic motion. It's repeating the same pattern over and over. And that's the same as if you compress the spring. Now the spring's pushing against you this way. You release it from rest. It goes firing down here until it reaches its maximum speed here. Now it starts stretching the spring, which pulls it back up until it stops it here, and then it goes back and forth and back and forth. So that's simple harmonic motion. Here's your maximum negative displacement, but your speed is 0 there. There's your maximum positive displacement, but the speed is 0 there. Here is your 0 displacement, but your speed is max here, going up or down, whichever way it happens to be going. So that's simple harmonic motion. Suppose that 10 centimeters is the maximum distance the ball moves vertically upward or downward from its equilibrium or rest position. Suppose further that the time it takes for the ball to move from its maximum displacement above 0 to its maximum displacement below 0 and back again is 4 seconds. So basically that's saying it goes from up here to here, then to here, then to here, then to here in 4 seconds. So it's 2 seconds to go here, 1 second to do here. 1 second, 1 second, 1 second, 1 second. 4 seconds to make it complete pathway. Okay? All right. Now let's think for a moment. What would your 10 centimeters be in terms of sines, cosines, that kind of stuff? Trig function. That would be your amplitude, 10 centimeters. That's how far it is from the maximum, from the equilibrium position. That was your amplitude. Guess what that 4 seconds is? Period, exactly. That's your period, 4 seconds, okay? Assuming the ideal conditions for a perfect elasticity, that means that spring is having no frictional losses internally, never happens, okay? But let's pretend that. And no friction or air resistance, never happens unless you're in a vacuum. The ball will continue to move up and down in a uniform, regular pattern, simple harmonic motion. From this spring, you can conclude that the period, or the time for one complete cycle, was 4 seconds. The amplitude, the maximum displacement from the equilibrium, was 10 centimeters. The frequency, I don't know if you remember this, frequency is 1 over period. So it'd be 1/4 of a cycle. See, this is 4 seconds per cycle, because it's 1 cycle. Seconds per cycle, so the frequency is 1 cycle per second. The reciprocal of that, 1/4 of a cycle per second. Because like I said, it went a quarter of a cycle in the first second, a quarter in the next second, a quarter in the next second, a quarter in the next second. So a quarter of a cycle each second. Okay? The motion of this nature can be described by a sine or a cosine function, and is called simple harmonic motion. Okay. Now, I'm going to tell you which I would have used. It says, suppose that 10 centimeters, okay. Yeah, 10 centimeters is the maximum distance the ball moves vertically upward. So you're starting from this position right here. Guess which trig function I would use for that? If your initial condition is 10 up, or your amplitude up, what trig function is that? Cosine, because it starts at 1 and goes down, okay? And that's exactly what this would be going. It would go down through the equilibrium position in 1/4 of a cycle, and then it goes to the negative amplitude, then back up, then back up. That's a cosine curve if I've ever seen one, okay? So that's the one I would use. Now, where would I use a sine? Well, if I started right here and took my finger and plucked it upward, then it would have been starting from here, and it went exactly 10 centimeters, and then back through here, and then like this. That's a sine function, because you're starting at equilibrium, going up to the max, and then down and up and down and up. That would have been a sine. So in this case, cosine. In this case, that's a negative cosine, because it's starting at the negative amplitude and then going up from there. Okay. But that's beside the point. That's just threw it in extra, no extra charge. Okay, simple harmonic motion. So here's a definition, bottom of page 331 of simple harmonic motion. A point that moves on a coordinate line is in simple harmonic motion when its distance d from the origin at time t is given by either d is equal to a cosine, what's that thing? That's an omega. That's a little lowercase omega in the Greek alphabet, okay? What we used to call b when we were doing, a cosine or sine bx, that would have been a b, now we're calling it an omega, okay? Or d is equal to a cosine omega t. I went with this one on that last example. Where a and omega are real numbers, such that omega is always positive, okay, that's good. That really screws things up if it's not. And the motion has the amplitude of, okay, thought that was the magnitude of the absolute value of A. The period is, just like before, 2 pi over what we used to call B is now your omega. And the frequency, of course, is reciprocal of that, which is omega over 2 pi. Or just 1 over the period. Now, just to give you an idea what we call this omega then. We call that the angular frequency. The frequency is a time frequency. The omega is the angular frequency. Because it does 2 pi in one cycle, 2 pi angles, in one cycle. So omega is the angular frequency of that. It's quite often you hear it called the frequency, but that's the angular frequency, not the time frequency. So, it says, write an equation for the simple harmonic motion of the ball described in this figure. I'm sorry, I can't hear you.
Did you ever send that email to Ms. McKenzie?
I can't hear you.
Did you send the email to Ms. McKenzie by any chance?
No, I forgot. I haven't done that yet. Does she still need that?
Yeah, I can't come to class until the email.
Okay. In my view, you can come to class, but I'll get the email sent if I can.
Okay, I have a draft on my laptop, so can I just get your email? And
Pardon me?
I have a draft that I typed up of the email, so if I just send it to you, you just have to send it to her. And
Well, it doesn't take me anything to send her an email.
okay, she's in my ear talking about it, and at this point, I mean, I'm doing everything.
Okay. Well, look, I'm in class right now. When I get out of class, I'll have 15 minutes. I'll send her an email.
Okay, thank you.
Okay. Okay. Sorry about that. Yes. Oh, it's time? Yuck. All right. We'll begin with example 6. Okay. Next time. I hope we get further than that today. All right. I said we were going to go fast, didn't I? Yeah, I really did. Okay, homework exercises here would be any of the odds, 5 through 11. They're all at Calc Chat. 9's at Calc View. Any of either 13 or 15, they're both at Calc Chat. 15's at Calc View. Any of the odds 17 through, my word, wow, 17 to 43, okay? Any of those odds, they're all at Calc Chat, okay? Then the simple harmonic motion, you can start working on those if you want to, 45 or 47, and those should both be at Calc Chat. We will pick up the rest of those next time. All right, good deal. Man, today's just flying by.